We are all used to now looking at a long list of risks from climate change, which obviously cover everything from human health to sea level rise, agricultural impacts, crop yields, impacts on ecosystems and biodiversity, extreme events, and so on. This nice paper just goes through few calculations to show that there are in fact a number of risks that are missing from the entire IPCC framework and assessment reports, and looks at the ontology of missing risks and then lists the typologies of where they actually come from. Ontology is basically like a evolution through life span, let's say birth, juvenile stage, adult stage, maturity, decay, death, and so on. It's usually used in biology, modeling fisheries, and so on. So here we distinguish between 5 categories of currently missing risks and suggest potential solutions on how to start integrating them into current and future studies. The categories below are based on the reasons behind their exclusions, and these reasons provide insight into how they can be engaged within engaged with in the near future. So they obviously include missing feedbacks, biophysical feedbacks, or simply model uncertainties, and so on. So let's look at some of them. Types of within process uncertainty. Within each process modeled to estimate a risk, aggregate uncertainty derives from various types of uncertainty in the assumptions. These are summarized below. So remember that IPCC itself defines risk as a multiplier of hazard, exposure, vulnerability, and now they've also added something called response. So hazard, let's say, comes from estimates from Earth system models, which have their own uncertainties. Vulnerability estimates depend on various indices like socioeconomic factors, per capita income, education, and so on. And the exposure, of course, depends on population densities, infrastructure, etc. So the sources of uncertainty are categorized here as scenario uncertainty, process parameter uncertainty, model uncertainty, trajectory uncertainty, and model inadequacies, so structural limitations of the model constructions themselves. Okay, so the common representation of each of these, for example, scenario uncertainty, we used representative concentration pathways, shared socioeconomic pathways, and shared policy assumptions, SPAs. And examples of uncertainty include business as usual scenarios, where we say we continue with current policies and not do anything, and where we end up in terms of warming, versus the intended nationally determined contributions, or what are now called nationally determined contributions, commitments from various countries, versus transitions necessary to limit warming. So countries commit to something, there is a business as usual, assuming we fail to meet our obligations and commitments, and then we go after emissions gaps and so on, looking at targets set for 1.5 degrees C or 2 degrees C warming by 2100 with something like 67% probability. So these intrinsically bring about some scenario uncertainties. Process parameter uncertainties include probability density functions across process parameter values. These run across all the models involved and all the processes being represented. So the equilibrium climate sensitivity distribution used in an integrated assessment model is an example. We have talked about integrated assessment models elsewhere. You can refer to those podcasts. But essentially, they have to provide climate as almost as an externality, external forcing, because they don't represent the details of the climate. They go after socioeconomic sectors, energy, agriculture, etc., and their impacts on future trajectories of emissions and so on. Equilibrium climate sensitivity is, of course, something that's defined as how much warming is achieved or attained when we double the CO2 and then keep it at that level till equilibrium. It's a kind of a theoretical framework, but nonetheless it's useful to look at how the system has been responding to increasing emissions since the Industrial Revolution, and if we double with respect to the pre-industrial revolution, where we will end up in a couple of centuries when the system equilibrates. Obviously transient climate responses are more important and interesting, but equilibrium climate sensitivity is what is used most often, especially for integrated assessment models. Model uncertainties themselves result from multiple models or perturbed physics explorations. Perturbed physics is where you change certain parameters like convective parameterizations, biological feedbacks on and off of the CO2 feedbacks from vegetation to climate, for example, and so on. And the example includes GCM multimodal and perturbed physics ensembles, intersectoral impact model in comparison project impact model, and process-based integrated assessment model intercomparison. So you have multiple models talking to each other or providing output in a linear way and then computing future trajectories. So model uncertainties are involved there. The trajectory uncertainty itself from multiple realizations from a model with perturbed initial conditions. So typically ensembles are done where you perturb some initial condition as you integrate, let's say, from the pre-industrial initial conditions to 2100, and then you keep perturbing initial conditions to see the what-if scenarios or the range of outcomes that are possible. Here the example is multiple model runs produced with individual GCMs or nonlinear models. So the nonlinearities or internal variability of the models produce these range of scenarios, like how El Niños change, how ocean meridional overturning circulations change, and so on. Model inadequacy, so structural limitations of our models, which basically common representations include descriptions of model limitations. The lack of a stratosphere or aspects of atmospheric chemistry in GCM climate simulations is a good example. The lack of time and temperature dependent climate sensitivity or types of climate impact in integrated assessment models are examples. To look at a bit more details, we are here looking at compounding uncertainty in climate risks estimation. So the process for developing risk estimates depends on several stages of analysis, with uncertainty compounding across stages. Distributions are shown here for an illustrative projection of changes to death rates in New Delhi. Axes are constructed so that expected value of the distributions of each scenario is aligned across subfigures. Okay, uncertainty in emission scenarios and their associated baseline socioeconomics contribute to uncertainty in climate changes, local hazards, impacts, and economic damages, including costs of adaptation. As climate risks can then affect emissions, for example, populations after death tolls. There are also feedbacks between these processes, further increasing the uncertainty. So tracking uncertainties across multiple models and multiple assumptions then misses out many of the risks. So here two policy scenarios are being looked at, SSP 1-2.6 and SSP 3-7.0. As you remember from RCP lingo, we get 2.6 and 7.0, which are the imbalanced in the net radiative forcing by 2100, and SSP 1 and 3 refer to this axis of adaptation and mitigation and various choices, socioeconomic governance choices you make, and where you end up with these. SSP 1.2.6 is the most benign in terms of the global warming targets. So if you look at the global populations that are affected in the social or assumed in socioeconomics, SSPs coming from integrated assessment models. Here you have the SSP 1-2.6, and this is the SSP 3-7.0. So big differences here. From the climate GCM, you have surface air temperature in Kelvin. So obviously the best scenario gives you a distribution of warming, the peak of which is below 2 degrees C, which is the goal of designing this scenario. And then the 3-7.0, which is not even the business as usual, it's the middle of the road, gives you a much larger tail warming, with peak being way over 2 degrees C here. Weather downscaling approach. So if you want to then take global models that are used for making projections and want to downscale to New Delhi, then you also are going to have uncertainties in terms of New Delhi temperature, which has a long tail here in the warmer scenario compared to the benign scenario. Physical impact quantification in terms of, let's say, change in death rate, deaths per 100,000, also quite different between the two, with this one at the tail end going to very high numbers. And of course there is the economic damages measured in terms of welfare loss as percentage of GDP equivalent, which have lots of overlap, but you can see that it's much higher for the warmer scenarios. Okay, so that gives you a sense of what could be missing. But you can then look at stylized channels by which risks can interact and compound. So we have climate environment system, which is, let's say, represented by the Earth system models, which have their own internal feedbacks like cascading tipping points. So if Arctic ice melts in a couple of decades, for example, the Atlantic meridional overturning circulation will be affected, the jet stream and the weather in the mid latitudes all the way down into the monsoon regions will be affected, and then they will affect other feedbacks like biodiversity loss, vegetation loss, agricultural crop yield loss, and so on. And then they create natural disasters which will act on top of exposure and sensitivity, but natural disasters themselves can have cascading disasters, what are called compound events, so droughts, wildfires combining with each other to provide disastrous health outcomes, or food security and water security issues, and those affecting the climate and environmental system. Exposure and sensitivity, of course, determine the social outcomes and impacts on socio-economic system, which can have cascading social changes or feedback to exposure and sensitivity through simultaneous exposure and sensitivity changes, as well as social outcomes can produce multiple stressors leading to all kinds of cascading effects, conflicts, displacements, food security, water security, energy security, and so on, and health, of course, as well. Okay. So the paper looks at hazards departing from furthest from recent historical distributions. So this is for the past, and it has a Z-score which determines its displacement from, let's say, climatology in terms of historical distribution. And the hazards looked at include flood, drought, precipitation variation, chill, and heat. So you can see chill occurs at higher latitudes and some in the middle as well. And precipitation variations are severe in some places, especially at the Sahel and some parts of India, whereas heat has exceeded the, in terms of a hazard, has exceeded historical distributions pretty much everywhere. So the entire map looks red, which obviously is very obvious. So the most direct impact of increased greenhouse gases, deforestation, land use, urbanization have been on the warming, and that appears as hazards that are exceeding you can think of these as exceedances from expected historical distributions. You can also look at those as population weighted distributions of future hazards. So you have climatology in the shaded gray areas, and how the distributions in terms of populations exposed to floods, droughts, precipitation variation, chill, and heat will change. And you can see droughts expose many more people in the future for this scenario of SSP 3-7.0 in 2050, and this is distribution compared to 1980 to 2009. And you can see heat, of course, is expected to get much worse, and then there is the additional factor of adding humidity and looking at dew point temperatures and seeing where we will exceed human capacity to get rid of the heat by sweating, or the limitations on the ability to sweat if dew point temperature begins to drop along with these temperature exceedances. There are many details which I have talked about before in other podcasts, looking at attribution of heat waves to climate change, for example, where mortality rates of heat exceedances in mid-latitudes are much higher than in global tropics, because people in the tropics are used to them and they deal with that in a different way than in mid-latitudes, and so on. So those kind of details have to be considered as well. But nonetheless, there is no real good news. With warming, you expect chill exceedances to drop, even though right now there are many cold exceedances happening in many of these higher latitudes. Okay, so the daytime and nighttime minimum temperatures are going to keep going up as well. Looking at probability distributions of populations affected by risk. Again, looking at here global mean surface temperature changes of 2 degrees C by 2100, 3 degrees C and 4 degrees C. As expected, heat waves will get worse with populations affected increasing. Similarly, ecosystem and food terrestrial biodiversity, which have massive spikes, whereas economics and welfare and productivity have lots of increased exposure of people to these losses. Displacements in terms of water stress. So with warming, you can see already with the middle of the line 3 degrees C warming, it's going to be as bad as 4 degrees C warming. River floods, agricultural losses, mortality, internal migrations, conflicts. You can look at the combined ones, okay, combined heat waves, river floods, wildfires and tropical cyclones. And for ecosystem and food, you combine terrestrial biodiversity, coral reefs collapse and agricultural losses with fisheries productivity changes, and that's where you end up. And similarly here, combine the economics and welfare from productivity, energy, mortality, conflict to end up here. You can see here the 4-degree warming has much higher percentage of population affected and water displacement as well when you combine sea level rise and sea inundation, internal migrations and external migrations. There are uncertainties in these which are indicated by the distributions to some extent, but we're talking about uncertainties in estimating risks. So this is about estimating missing risks by paying attention to such details in terms of how these things combine with each other to produce a larger fraction of population combined, for example. And you look at interpolated population affected curve as a function of warming. So you can see population affected will keep on increasing, and then at some point we are going to saturate, basically because you are going to have affected pretty much everybody on the planet. Okay, so how to integrate these into future assessments to make sure that we don't miss the risks that are created by these interactions, feedbacks, and simply model deficiencies and so on have to be taken into account for future assessments and for planning, mitigation, adaptation as well, and feeding into the shared socioeconomic pathways or shared policy scenarios as well. Okay.